Okay, back at it for another short video, trying to keep them short and sweet. Just get the major topics in front of us so that we can have as much time as possible to try to integrate them, understand them before the end of the term. And one of my major goals, as I stated at the beginning, back in late December, mid-December, when we started up, was that I was hoping to help you learn to think mathematically. Now, I don't have a monopoly on the definition of what that means, but to me, it means learning to recognize patterns and learning to make more complicated situations simpler and easier to understand. I think that has intrinsic value from discipline to discipline. And so I think there are neural pathways that you want to try to connect that strengthen your ability to see things more easily. So let's start with a problem we've already got in front of us, how to find the area bounded by two curves. And then we'll build off that. So once again, we're extending our ability to work with differentiation and integration. So there's nothing new here. Really coming at the same major topic, integration, same major topic from a different perspective. And hopefully some of these perspectives start to click a little bit. And you see that we're doing the same thing over and over and over again. All right, so let's take a situation that hopefully you can follow. Most of you, well, a number of you can do this already on your own. Some of you are still struggling to get some of the product rules and quotient rules and things like that down. That's on you. We're moving on. All right, those are simply memorizations and practice, and nobody can do that for you but you. So if you want to get those right, then get to it. Right now, we're looking at how to find the area between two curves. Let's have the curves be x equals 0, which is the y-axis, y equals 5, constant, y equals the square root of x. They obviously intersect at the coordinate 25, 5. Okay, so we're going to use vertical rectangles. It's like an infinite number of Riemann sums. I put some space in between these. It's like laying a carpet horizontally. And so we have to define each y value, and each y value is depending upon the x at an instant. All right, so for instance, if x was 9, then we know that this dotted line is 3 units high. We know that the top function is 5, and so the length of this rectangle would be 2. Okay, nothing new here. We've been talking about this in class now for at least a week, if not longer. And so here's the integral from a to b. In this case, is from 0 to 25. And what's the mantra for finding area between two curves? If we're using vertical rectangles, top minus bottom. The top function was 5. The bottom function was the square root of x. Now we have a basic integration. Add 1, 3/2 divided by 3/2, 2/3. And, rate change of 5 comes from a linear function. And so we can see that when we drop a 0 in, we don't have to do the second half of the fundamental theorem. So 5 times 25 is 125. We take the square root of 25, which is 5. 5 cubes, 125. 2/3 of 125 from 125 gives us 1/3, 125 over 3. Right? That you should have been able to follow that. We've been doing that right along. All right, so what's new? What's new is there's an easier way to do this problem. And that's not to add up horizontal rectangles. Vertical rectangles, but it's to add up horizontal. And we're going to do that over here right now. All right, let's see if we can move this down just a little bit further. All right. Yeah, I think we can see all of that. All right, so the question is, what if I were to stack these vertically? And remember, that dotted line is an x distance. So we have to use the y values. Really, we're creating a function in terms of the y values to get us those x distances, because they're going to be the lengths of the rectangle. So how do we do that? Well, if y is equal to the square root of x, how do I isolate x? It's y squared. So I can call this right-hand side y squared. And what's the x distance on the y-axis? Well, that's 0. All right, so we have these x's come from y squared, and this side here is 0, so x equals 0. So what do we have? Instead of doing left to right, we're doing bottom to top. And so the mantra is top to bottom on the left side over here. Over here, it's right to left. Okay, so we take the right-hand side to the left-hand side. So if we were on the x-axis, and this was 9, and this was 7, what is that distance? It's 2, right? Right minus left. So what's my right minus left in this case? Y squared minus 0. Yeah, you can see that. All right, but we're going to go vertically from 0 to 5. Okay, so we can integrate y squared dy. It's just add 1, divide by that number. So y cubed over 3 from 0 to 5. And we can see that if we put 5 in, we get 125 over 3. And if we put 0 in, we get 0 over 3. And so what is the area if we do the integration in terms of y? 125 over 3. What was it over here? 125 over 3. It's actually easier to do it in terms of y. So that's a new topic. I probably should have had another one that we could have done right on the spot, but I think that'll suffice just to get us started. All right.